we will start talking about what's called graph theory. Now, the use of the word graph here is not the same as the graphs you have seen, for example, in calculus and so on, when we talk about functions or sin x or cos x or other kinds of functions. So, this is a sort of a pictorial depiction of a function and the values it takes. For us in graph theory, a graph will mean the following. So, let us define what we mean by graph now for this portion. So, a graph G is the following. Informally, it is a collection of points, finitely many points, and with some lines or connections between them. So, what I need to do is to draw some points 1, 2, 3, 4, 5 here, 5 points, and then I join some pairs of them by lines. So, for instance, here what I have drawn is a graph. So, a graph G formally is a pair comprising two sets V and E, where V is a finite set and this finite set is usually called the set of vertices of the graph, and the set E is the following. So, E is like we should think of them as these connections or lines between pairs of vertices, and formally E is a subset of what? Of the set of two element subsets of V. Okay. So, let us maybe define that first. So, let me take some larger set. So, let me call it omega. Let omega be the set of all pairs of elements, or let me call it two element subsets of V. Okay. So, what does that mean? What are the elements of omega? For example, it has got 1 2, 1 3, 1 4, etc. So, all possible pairs that you can think of writing, and I write them as subsets. So, this is the entire collection of elements in omega, and observe omega is, how big is omega? Well, it is from the 5 points I need to choose 2 points in all possible ways, or pairs in all possible ways. So, the cardinality of this set omega is going to be if I choose 2. Okay. So, there are those many possible lines that I can imagine drawing between these pairs of points, but I do not want all those lines. When I talk about a graph, I take these vertices and I take some subset of these lines. Okay. And E is a subset of this set omega of pairs of points. Okay. And this set E is, elements of E are called the edges of the graph. Okay. So, graph basically has two sets. First, the set of vertices or the points, and a collection of edges or connections or lines between some pairs of points. Okay. So, that is what a graph is, and informally when we try to describe the edges, we will not always keep writing this sort of notation with pairs, set with 1, 2 and so on. So, sometimes we just tend to abbreviate it. We say, okay, the set of edges, for example, in this case for this graph, there is an edge connecting 1 and 4. So, I will just write it as 1 4, there is an edge connecting 1 and 5, 2 5, 2 3 and 3 4. Okay. So, there are 5 edges, and those are the 5 of them here. Okay. And again, when I write 1 4, I could have also written it as 4 1, for example, and that is the same thing. Okay. So, anyway, so that is what a graph is informally and formally, in fact. Now, the thing that we often do is, rather than this formal picture, rather than thinking of it as vertices and edges, we often try to think of it in terms of pictures, and when we draw graphs we have to be wary of one thing. So, for example, let me draw a graph with 4 vertices. So, here is a graph, and let us say there is also an edge connecting 1 and 3. So, this graph that I have drawn here, now let me draw yet another graph. Okay, now my vertices are numbered a little differently, 1, 2, 3, 4. So, here is another graph, and maybe there is here is one more. Okay, so what I have drawn are 3 very different looking pictures, but if you sort of stare closely at all of them, you will observe that these are actually the same graph. So, all these 3 are in fact the exact same graph. Okay. Why is that? Well, remember, a graph finally only means I should keep track of what are the vertices and what are the edges between them. So, here if you look, what is the vertex set? The vertex set in all cases is just the set of 4 vertices labeled 1, 2, 3, 4. So, in each case we will just see what the edges are. So, in the first case here we see what are the edges. So, there is an edge connecting 1 and 2, 2, 3, 3, 4, 4, 1 and 1, 3. Now, here again there is an edge connecting 1, 4, 4, 3, 3, 2, 2, 1, 1, 3. Now, here again it is the same thing, 1, 3, there is an edge 2, 3, 1, 4 and 3, 4. Now, if you see, in all cases it is the exact 5, the very same 5 edges which appear in all these 3 pictures. So, from that point of view, all these 3 are actually the same graph, but these are different ways of drawing, if you wish, the same underlying graph. And this is one thing that one has to be careful about, that when you see different looking pictures, they may not always be different as graphs, they may actually represent the same underlying connections between pairs. So, what matters is which pair is connected and which vertex is connected to which other vertex. That is the only piece of information that defines a graph. Now, the other important point is when we draw edges, we can draw them whichever way we want. So, here for instance, these 2 edges meet here. So, this edge 1, 2 and 1, 3, I have drawn them in some strange way where they seem to have some point of intersection in the middle. Now, such points of intersection do not really mean anything. Okay, so, you should not think of these like they are roads connecting cities or something like that, where when 2 roads meet somewhere, that becomes another point of interest. So, that is not the case. When graphs are drawn and it so happens that 2 lines intersect, that does not really mean anything from the perspective of the graph itself. This point we just ignore. So, this point we just ignore, and there are really only 4 vertices even in this case, 1, 2, 3 and 4, and the connections are just the lines that we have actually indicated between them. Okay, so that is an important point to keep in mind when depicting graphs or drawing graphs. Okay, now the very important question of where do graphs really appear, or why should one really be worrying about these configurations of points and connections between them? The answer is that they appear in a very large number of areas, not just in mathematics itself. So, they initially came up in various parts of engineering, for example, in circuits, in the study of electrical circuits. In the modern day, they arise when one tries to understand what the internet looks like. You often view it as a collection of web pages with links between them. It appears in other fields of science, for example, in chemistry. It appears in study of languages, linguistics, in biology, in genetics. in many fields of engineering, for example, in transportation, studying optimization, operations, research, and so on. And of course, in addition to all this, it appears in very many areas of pure mathematics. Many fields of mathematics actually have interesting structures which can be modeled as graphs. So they occur in lots of places, and they have very many applications. In all these instances, you often think of graphs as modeling relationships between a certain collection of objects. Okay, so those edges which depict the presence of some sort of relationship between the two vertices that they are connecting. Okay, so here's sort of another example. So I mentioned the internet. So let's just look at these two instances. So a graph, for example, could model a railway network, for instance. So train networks or more general networks could be modeled by graphs. You could think of the different cities or towns as being your vertices, and whenever there is a direct train, for example, between two of them, you indicate that by just putting a line joining those two. So this presence of a line will mean there is a direct train which will take you from point 1 to point 3, for example. And between certain pairs of vertices, maybe there are no direct trains. You have to switch trains, take a connecting train from some other places, and so on. So this could, here's some example, and you might sometimes want to ask questions like, so suppose I want to, so let me say this is my network of trains, and I want to go from one point on my network to another point. So I want to go from, say, point 1 to point 6, and so the sorts of questions you can answer are, which route would take you from point 1 to point 6 by using the least number of trains. You have to make the least number of changeovers to go from one to the other. So that's like saying, in this network, what is the shortest path which will take me from 1 to 6. So for instance, I could go from 1 to 3, take another train from 3 to 4, and change again and take a train which will take me to 6. That's a path of length 3, but there is a shorter path. I could just go to 5 and then go to 6 directly from there, right? So in this case, there's a path which will just take you there in 2 steps, and so this allows you to answer questions like, what's the quickest way to get from one point of your network to another. The other sort of example is the internet itself, which one models as, so what is the internet really? You can think of it as a large number of web pages. So imagine, so we model each web page as a vertex of our graph, and we sort of indicate relationships between web pages. So what relationships can you have? Well, a given web page may link to another web page, right? You may find a link from one web page to another one. So maybe certain web pages link to very many others, and so on. So okay, it's a very complicated graph, if you wish, of web pages and links between them. So you can, there are billions of vertices, for example, and billions of connections between them. But interestingly, this way of modeling web pages and links actually has very important practical applications. So a lot of web search or search engines like Google and others fundamentally use these relationships to provide the most relevant results for a given search term. So web search, for example, is largely built on this particular model of thinking of each web page as a vertex and each link pointing from one to the other as a edge of the graph. So these are all very important practical applications of graphs themselves. So what we will consider are some nice mathematical aspects of this structure of graphs and answer some simple questions about graphs, for example, about paths and connectedness and so on.